Giving you minutes when you are.
So each 5 minutes?
15, 5. When you are missing 15 minutes left.
Okay.
10 minutes
Yeah,
left,
yeah.
5 minutes left. And then
Cool.
And then also, when answering questions, just repeat them.
Repeat them?
Microphone.
Yep. Got it. Okay, so we're not going to sit here. It's only going to be there. Yep. The keys work, it just doesn't replay.
Okay, so we have Dmitry Marshall and Marcus Sigl-Reitmeier. Please forgive me. They're going to be talking about the portable graphics abstraction in Rust. Please give them a warm welcome.
where are you connected?
HTML?
Yeah.
So, hello everyone. I'm Dmitry Malyshev, a graphics engineer at Mozilla. I work in Firefox web browser, and before that, I worked in the AA game dev industry, which inspired me to start writing a graphics abstraction layer in Rust. And this is Marcus, who joined us recently to rewrite it, and that's what we are going to talk about. The idea is to have a single abstraction layer to run on all the platforms that we have. Unfortunately, the graphics API have been branched out. We have Microsoft pushing the DirectX 12 in the Windows ecosystem, and we have Apple pushing for Metal. Everything else is adopting Vulkan quite successfully, including the Android, the most popular operating system. And OpenGL is still alive as well. And we want all of those to be available through a single interface in Rust that is hopefully safe and fast. It started in 2014, and the legend is we had 3 threads at the beginning, and then we were fast-tracking through the evolution of the APIs as the native APIs did. So first we got command buffers, we got rid of the threads, and then we followed with resource views, pipeline states, eventually getting the D3D11 and Metal backends. And then somewhere around 2017, when we started first talks about integrating into WebRender, it appeared to us that even though we already had the core layer split out of the higher level rendering, we still weren't zero cost enough. So we decided to go lower level. We decided to implement the core to be completely zero cost. And that's where Marcus comes in. This is the main roadmap of our work. And if you are taking one thing from our talk, then that should be this slide, I believe. At the center, you see hardware abstraction layer. That's our new core. That's the name of the new core. It's Vulkan-like Rust API, very low level, quite unsafe, that different graphics backends implement, including Vulkan, Metal, D3D12, and OpenGL. These are the backends that we already have now. And we are getting D3D11 soon enough as well. The clients of the hardware abstraction layer are many. Aside from the user apps, we have the Vulkan portability layer, which we are talking about a little bit later. We have the Warden test framework to ensure no regressions in the graphics tests. And we have a web GPU prototype based on Servo that's using that. A little bit more about the Warden test framework. It consists of 3 parts. First one is we are able to describe graphics resources and passes in readable source, which we use the Rusty object notation for. It says, here's my images, buffers, here's what I'm going to do this with them in the following passes. And then we can load it all with a particular graphics backend so that it instantiates the resources on the GPU and creates the command buffers to implement passes. And then we have a ref test framework, which has very simple ref tests defined, and it runs the graphics passes on the specific backends, compares the expectations with the tests. This is an example of the resources. We have an image with a specified format and dimensions. We have a rendered pass with one attachment and one subpass, just as an example of roughly how it looks. This is the contents of the pass. We have setting the viewports, the pipeline, and drawing a single triangle here.
Okay, so then why we want to actually use Rust instead of, for example, C++? There are a few nice bits of Rust compared to the basic concurrency, all const, new features like pattern matching. There's send-sync, which basically tells you that every object in our API is send-sync, so you can access it from all threads and concurrently. And there's also immutability, which we use to say, for example, you can change this object or you can't. And it also encodes if you need to externally enforce single access, because, for example, some objects can only be accessed on one thread or at one time. So if you see mutable access, you usually indicates that you need to externally synchronize your object. Then traits and associated types, which we use quite heavily, which you will see later on. And we split all the things into multiple repositories. For example, one repository is the hardware abstraction layer, and then for each backend we have an additional repository. And for okay, great. So what we are currently missing is, for example, non-exhaustive enums, which are basically required as we also provide a higher level abstraction for this Vulkan portability implementation. And there are cases where Vulkan could return us enum values which we not really know at the current time of implementing, which could come from a future driver, which would return us this new enum values. Then struct alignments in shaders, which it happens every day that we misalign some shader struct because there's one page of Vulkan specification which basically says how you need to align your fields, and it's usually you do something wrong there. Then const generics, which would give us the possibility to use arrays, fixed size arrays more often in the library interface. We basically expose a quite generic interface using into iterator, but yeah, fixed sized arrays would help quite a lot for the user side to looks a bit better. And exclusive cargo features. At the moment, you could do something like I want DX12 and Vulkan to run at the same time somehow, but it usually will mess up here, and you usually only want DX12 or Vulkan. So the backend trait is our main interface. It's one large trait you have to implement if you want to implement a backend. We basically divide it into dispatchable objects like the device or the command queue, which you can call functions on, and the basic resources like shaders, a buffer, image, which you usually just pass around and create and delete. So for the roadmap 2018, we would like to become a Mozilla project because we want to integrate into WebRender and also into the Web GPU part, which Dimitri will talk about. And one side project is Vulkan Portability. It's an initiative from Vulkan, from Kronos, where they try to do all the three backends, Vulkan, DX12, and Metal, and provide one API subset from the Vulkan API, which can map to all these three backends. And our goal is to implement the Vulkan portability layer using our hardware abstraction layer. And we currently can already pass a few examples, like triangles or pipeline example from common samples, from Vulkan samples. And we are aiming at implementing or hooking up the Vulkan conformance test. Yeah. We try to hook up the Vulkan conformance test suite and run the tests against our hardware abstraction layer. That's how it looks from our side. We basically have our hardware abstraction layer on the bottom, which is the GFRS side, and on the top we have the portability layer. And you can interface it using a driver implementation or using a static library if you want to directly link it from a C library. Okay.
So a little bit more information about what WebGPU is. It's a W3C working group, which Microsoft, Apple, Mozilla, and Google are part of, and as well as a lot of independent actors, that is trying to design a new API to provide newer, lower-level concepts onto the web for faster interactive applications on the web. And there's been a lot of discussions over what the next gen API is going to be, and I'm a part of the group, and we don't seem to have a lot to agree on so far. Everyone is sort of pushing in a different direction. So our position there is to have something either exactly like Vulkan or very close to Vulkan. Based on that, we developed a prototype that is using Servo, but adding a new WebIDL-based API that has basically Vulkan calls in it. So you can go that low level and create your pipeline barriers and descriptors on the web using JavaScript or WebAssembly and run it in the browsers, which is currently a very specific fork of Servo. Our future plans with the web GPU include trying to get a native application trans-compiling to the web using WebAssembly. So a native application using Vulkan to be compiled using WebAssembly for the web on the browser, so that it just runs in the browser, so that you don't need to learn a new API, that you can just use Vulkan on the web. Now a little bit more about the ecosystem that we have. And since we seem to have a lot more time left, we're going to start on each of them closely. There is a few engines in Rust at the moment. None of them is mature enough, but they're very promising, namely Good Game Easy, Amethyst, and 3RS. All of those use the older JFXRS at the moment, where Amethyst is already transitioning towards the new hardware abstraction layer. It's extremely promising to us since they not only are porting to the hardware abstraction layer, they're bringing the higher levels for us to use. For example, a library that manages memory for you so that you don't have to care about particular memory types that the driver exposes. You just say, oh, I want this buffer, and the library handles the actual heap management and allocation of the memory from the driver for you. Or a frame graph sort of thing, which allows you to describe all your graphics workload as one big graph, which is then automatically deriving the dependencies, the memory barriers for you, and possibly schedules it to run on multiple hardware queues for execution in parallel. So this is what Amethyst folks are bringing on the table, and I'm sure Good Game Easy and 3RS will follow and use hardware abstraction layer in 2018. Other than that, we have a very interesting plans with Vulcano as a project that we are often being compared to. In fact, now the comparison doesn't make much sense because we are lower level. We are implementing Vulkan, and Vulcano is based on Vulkan. So what we want to do is to let users use Vulcano on top of GFX hardware abstraction layer. So in a sense, it's a drop-in replacement. The users will not need to do anything, and they will instantly get access to Apple and Microsoft platforms, potentially Xbox One as well. So that's something that we are working on right now. And finally, WebRender is a Mozilla research project that is currently being integrated into Firefox. It is in need of better control of the latency resources and more direct access on Windows platforms for example, playing a video efficiently. So our Vulkan portability or graphics abstraction layer makes perfect sense to be a part of WebRender, and we are already working on that. We have a group in Szeged University in Hungary that's porting WebRender, and they have an exciting progress so far. So they translate the shaders automatically, and they already run our ref test framework. So we're looking forward to see WebRender running on HAL this year, potentially upstreamed as well to Firefox. And we have a very lively Gitter chat, which does not have a link here. But we have also a blog post, and you can just jump on the project page on GitHub, and it will have all the links that you will ever need. We are always happy to answer your questions, and right now I'm going to run a demo that Marcus have written. The demo features quite a few compute shaders and some rendering as well, and it's fairly complex. It simulates Oceanware, and it runs exactly the same on D312, Metal, and Vulkan, using the same shaders and the same API calls. So that is it. We're ready for questions. So the question is, why do we consider it a zero-cost abstraction layer? It's zero cost in a sense that if you want it to be backed by Vulkan, then we don't do any heap allocations, and we don't do any smart pointers management for you. It has explicit allocation and free calls for resources. Of course, there is certain warts that we have to do in order for the same API to run on D312 and Metal. So this is not exactly zero cost in that sense. This is as low cost as we can afford, but this goes in line, not in our own reasoning, but more in line of the Vulkan portability technical subgroup and the design that we're doing as a part of the group. So it's very little minimum overhead. We can't afford any extra GPU work for whatever we are doing. Is your question that we are losing quite a bit of command buffers in metal?
Well, potentially you don't have the command. You know the way that you can use things the BK fence and you put it into say that you want to reuse the command buffers in Vulkan. And you can't do that in metal, right? That's a real performance loss if you can't do that in metal.
Okay, so the question is how do we deal with the performance loss from not being able to reuse command buffers in metal? That is very unfortunate, and what Molten VK is doing as one of our competitors technically is having like a software list of commands built up independent of the hardware list. So I don't think we have that implemented right now, but that's the plan right now. Yes. Are there any plans for the graphical UI toolkit? We are extremely busy with making sure that the hardware abstraction layer, like the lowest level of abstraction, works. And our next steps are more in terms of getting the frame graph sort of libraries or the memory management libraries solid before we can think about the UI. However, I expect Conrod to be able to be ported on JFX HAL eventually. It's a graphical UI toolkit for Rust, as well as our friendly Amethyst folks are likely to come up with something too. So we hope for your help.
How do you handle shaders? I mean, can I write one shader and then you like transpile to the other languages like for Meta and stuff, or I have to write different shaders for every backend?
So historically, before the rewrite, we required. Sorry, the question was how do we handle shaders with regards to different platforms? Historically, we required the users to provide all the shaders for the backends that they use, like separate shaders for Metal, OpenGL, and G3.11. After the rewrite, as we are going for the Vulkan portability goal, we only accept SPRV. And from SPRV, we generate all the backend-specific shaders. We patch the logic like coordinate systems and descriptors, IDs, according to the specifics of the backend that we are translating the shader into. We're using the SPRV cross as like a helper library to do that. And our future far plans would be to have a Rust alternative to that as well, since that's the biggest non-Rust component that we use right now. So right now, you supply your shaders in SPRV. Of course, the most convenient way to do that would be to write it in GLSL, say 4.1, and then have them convert it using GLSL to SPRV. That's what Warden Test Framework is doing, at least. You write your shaders in like GLSL and it tests them against SPRV.
You talked about web GPU. I mean, and you're talking about Vulkan. I mean, that's kind of a long way from WebGL. WebGL, I mean, the shaders are restricted to where you can like certain loops and everything. I mean, all of that. Are you saying that will go away? You kind of clean exposure of Vulkan?
So the question is how does WebGPU is going to expose Vulkan given that WebGL is way higher level? So yes, it's a hard question, and Vulkan is a hard sell for multiple reasons on the web, not only because it's low level, but all the consequences from it is like it's easy to build a user signature based on what you query about what device can do, and on the web it's not safe, and there's a whole lot of concerns that not only Vulkan, but in general, going any low level on the graphics side to slightly start breaking the rules of the web. So we're trying to find our philosophy there, and our priority is getting like the maximum performance of the web. Where we heard